Now Newton's law of cooling is given by this here. Theta equals theta 0, that's sub-zero. Theta equals theta sub-zero times e to the power minus kt, where the excess of temperature at 0 time is T degrees Celsius, and at time t seconds is 0 degrees Celsius. Not sure about might be a typo in there, but not sure. Determine the rate of change of temperature after 40 seconds. Right, so rate of change. Where's that there, right? Rate of change. Right, that always means differentiation, right? When you see rate of change. Temperature after 40 seconds. Given that theta equals 16 degrees and k equals this here, right? K will be a constant. T will be a variable that will vary depending on the time, or that varies, that is the time. So that's a variable, right? And I'm thinking that theta sub-zero is that's a constant. That's going to be the temperature when t is 0, right? Because when t is 0, e to the power minus k times 0, that becomes e to the power of 0, right? When t is 0. Anything to the power of 0 equals 1. So when the time is 0, theta will equal theta sub-zero multiplied by 1. So at 0 time, when t equals 0, our temperature theta will equal theta sub-zero. Right? Now, determine the rate of change of temperature after 40 seconds. So that's going to be T, given that theta equals 16 degrees. Now, I think that needs to be theta sub-zero there. Theta sub-zero is 16 degrees. That'll be our kind of starting temperature. And this 0 time here, I think that should be sub-zero as well. Anyway, we'll differentiate. So it's going to be d theta dt equals. Now, if you look up the log tables there, you see that in this type of setup, if it's e to the ax, right? If that equals a function, if that's a function, the first derivative, f dash of x or dy dx, will equal, the a comes down in front and we keep this structure e to the ax like that, right? That's a rule that's on page 25 of the log tables. So we're going to apply that here. In our case, it's not a, it's going to be minus k. So the minus k will come down in front, and our theta sub-zero, it'll get multiplied by our theta sub-zero, which is going to be a constant, because this is the temperature when t equals 0, times e, and we keep it up there, minus kt. So this is d theta dt, this is the delta and delta, the change in temperature over the change in time. It's like miles per hour, kilometers per hour. So that's the rate of change of theta, or temperature, with respect to the change in time. So this will give us how fast the temperature is changing with respect to time. And we can plug in values, like they've given us there, k, when k equals minus 0.03, and t will equal 40 seconds, and theta, you see, it has to be theta sub-zero in my opinion, because it won't go in, theta doesn't fit in there as theta sub-zero. It's a different thing to theta. Theta sub-zero is 16 degrees Celsius. So we're going to plug those in to get the rate of change of temperature after 40 seconds. So d theta dt will equal minus k. Now we're told that k, so it's going to be minus k. So k is minus 0.03, so we have to be careful with our minuses. And 16 for theta sub-zero times e, which is just a number on the calculator. Let's right? We can think of it like this just as a number on the calculator. Minus k, so that's minus 0.03 times t, which is time, 40 seconds. So minus times a minus gives us a plus, so that'll be 0.03 multiplied by 16 times e to the power of minus, there it's going to be a plus again. Now I'm going to multiply 0.03 by 40. I get 6 over 5 or 1.2. So that's e to the power of 1.2. And tidying up further, I'm going to multiply this first bit, 0.03 by 16, 12 over 25, or 0.48. 0.48 times e to the 1.2, right? And we can bang that into the calculator, no problem. So 0.48 multiplied by e, there is shift and the ln key, and 1.2 for the power, press equals. I get 1.59, so to 2 decimal places, the rate of change, right, to 2 decimal places I get 1.59. So I get 1.59 for, that's rounded to 2 decimal places. And what are we talking about? We're talking about theta over t. Theta's, so it's going to be theta's per t, right? Well, it's not really that, it's going to be degrees. That's going to be, let's get the eraser here. It's going to be 1.59 degrees Celsius per second. That's kind of like the acceleration, or is it? No, it's the speed. It's the rate of change of the temperature with respect to time after 40 seconds. No, I'm not sure about this being right or wrong, but anyway, there's a lot in there that is right, hopefully. So you can get back to me if you have any thoughts on that.